Example number 13, we're going to evaluate this double integral, and it happens to be an improper integral. That's because one of the limits is infinity in this case. All right, so we would evaluate the double integral the way we would usually do, evaluating one integral at a time. However, when it comes to the integral where it gets the limit of integration of infinity, we need to use the limit notation. That's something you might recall from back in calculus 2. In the meantime, we're going to integrate the innermost function, with respect with respect to y rather, and we're going to integrate the exponential. So that's going to give us the integral from 0 to infinity of 1 over 9 plus 4x squared. That's going to be 1/5 times e to the 5y. And evaluate that between 0 and 3. And don't forget the dx. Well, I'm going to take this 1/5 out of the integral. That's 1/5 integral from 0 to infinity of 1 over 9 plus 4x squared e to the, let me do 5 times 3 minus e to the 5 times 0 dx, and that'll be, that's going to give us 1/5 integral from 0 to infinity of 1 over 9 plus 4x squared. Well, e to the 5 times 3, that's going to give us e to the 15 minus e to the 5 times 0, which is e to the 0, and recall that e to the 0 equals to 1, which is that times dx. But this e to the 15 minus 1 is just a multiple constant. I'm going to take it outside and multiply it with the 1/5. Well, that's 1/5 times e to the 15 minus 1 integral from 0 to infinity of dx over 9 plus 4x squared. Okay, so here is where we get to the improper integral. And well, recall that we cannot just integrate and evaluate upper limit minus lower limit for when the limit is infinity. So we need to use the special limit notation, because again, it's not like we can do arithmetics with infinity. So infinity is just an idea of something that they get big and big, but and we can do operations with something that it keeps growing and growing and growing. Okay, so let me write it down as a limit notation. That is 1/5 e to the 15 minus 1 integral, oh, not the integral, that is limit as b approaches infinity of the integral from 0 to b dx over 9. Well, actually, I'm going to write this 9 plus 4x squared as 2 squared plus, no, not 2 squared, rather 3 squared plus 2 x quantity squared. That's because from here we can already identify that we're going to deal with an arctan rule problem. And now that we identify such pattern, well, let's identify our a equals to 3 and our u equals to 2x, for which we're going to do the du equals to 2 dx, where dx equals 1/2 du. All right, and then we also need to change the limits of integration from the world of x to the world of u. That is, u of 0 equals to 2 times 0, which is going to be still 0. However, u of b, the upper limit, that equals 2 times b, where that's going to be simply 2b. Okay, so writing down our integral within the new limit, well, that's going to leave us with 1/5 e to the 15th minus 1 limit as b approaches infinity of the integral from 0 to 2b, the new limit, of 1/2 du over a squared plus u squared, which is our arctangent form. Okay, so let me take that 1/2 and multiply that with the 1/5 outside. That's going to leave us with a 1/10. So that equals 1/10 e to the 15 minus 1 limit as b approaches infinity of the integral from 0 to 2b of du over a squared plus u squared, where the integral of a squared of du over a squared plus u squared, that's our arctan rule. So that's going to give us 1 over 10 e to the 15 minus 1 times the limit as b approaches infinity of the quantity arctangent, or rather 1 over a arctangent. Don't forget the 1 over a. 1 over a arctangent of u over a. So that's our arctan rule. And evaluate that between, what's that? 0 and 2b. Well, so from here we can back substitute our a. All right. So that is 1/10 e to the 15 minus 1 limit as b approaches infinity 1 over a, which is 1 over 3 arctan of u over 3 from 0 to 2b. Okay, so let's do upper limit minus lower limit. Let me keep going down. I don't think I'm going to have enough space here. Okay, so that's 1/10 e to the 15 minus 1 limit as b approaches infinity. Oh, okay, actually this 1/10 times 1/3 is going to give us a 1/30th. Okay, much better. So let's simplify this, and that'll be okay. So arctan of upper limit 2b over 3 minus lower limit, that's arctangent of 0 over 3. Okay, so, well, arctangent of 0 over 3, well, that's going to give us 0 because arctangent of 0 equals to 0. However, arctangent of 2b over 3 as b approaches infinity, well, that's going to ask us to compute arctangent of infinity, but we know arctangent of infinity equals to pi over 2. In fact, that's the upper horizontal asymptote of the arctangent function. Well, that's going to give us then, as a result, 1 over 30 e to the 15 minus 1 times pi over 2 minus 0, and we'll just multiply, okay, pi minus 0, pi over 2 minus 0, it's simply pi over 2. And you might want to multiply pi over 2 times 1 over 30. That's going to give us 1 over 60 times e to the 15 minus 1. All right? And don't forget pi. Well, let me actually multiply the pi right here. That'll be better. All right, and that's final answer. Well, because this double integral involving at least one of them an improper integral, since we got as a result a real number, no, we didn't get a DNE or an infinity. Well, since we got a result, well, then the integral converges. All right. So that's what the instructions mean by discuss the convergence. So if we get an actual number, well, it converges. Otherwise, you get a DNE for the limit, well, the integral diverges. All right.